Hi guys, welcome back to my channel. So on this video is basically to introduce you to Foster 1, Foster 2, Cauer 1, Cauer 2, and how to arrange your functions in order to find any of the Foster or Cauer form. So first of all, we need to know that once you're having a function to be given as set of s, you know that since you are not having an s term, since it's a constant, this a is a constant, then the value of the component to be a resistor, right? This is an r, be a resistor. So if you're having another function to be given as 1 over cs, then this constant here, because it's having an s term below, the s term is not on top, it's below, so the constant number you're having here will be the capacitor. You can sometimes see something like this over s, right? All you have to do is divide both the numerator and denominator by a. So divide this by a, divide this by a, then you can sometimes see something like a over s, right? This is a number that is not 1, is not equals to 1, right? So all you have to do is divide both the numerator and denominator by a, then you have something like 1 over as, right? The s is on top, right? The s, so this 1 over a is still this c, right? So is also equals to 1 over a, which is c, which is the capacitor. So that's it. So you can also have ls, which is what? An inductor. Because it's z of s, this will be an inductor, right? So you have to be an inductor. So in case of y of s, if we have something like a, then it's going to be what? 1 over a, right? The value of the resistor is going to be 1 over a. So if you have something like 1 over ls, right, it's going to be what? This value here, which is what? L, the inductor, right? If you have something like cs, it's just this constant here, the coefficient, which is what? C. For this, also similar to this, you can also see something like a over ls, a over s. So since it's y of s, you have the divide both sides by a. It's just similar to that. Since y of s, it will be an inductor, but all you have to do is divide both the numerator and denominator by a. You have something like 1 over s over a. It's still the same as this, right? 1 over s over a, which is just what? This can also be written as 1 over es, right? Which is equals to, this is what? Just ls, right? Which the value of the inductor is going to be what? L, which is just this. So don't be confused about that. So these are just used to find the value of the components after the network synthesis, after doing all the necessary stuff you have to do in Foster 1 or Foster 2 or Cauer 1 or Cauer 2. These are just used, so based on the results you get, these are used to find those component values. So now the next step is to show you how to identify if a function or a given a function, either z of s or y of s, will have a pole at infinity or at 0, because I think that confuses most students a lot. So I'm going to try to clarify that in this video, so you'll be able to know whether the function, before you even start the synthesis, you will know whether the function is going to have a pole at 0, which simply means the components at the beginning, like a component at the beginning, maybe an inductor, and you have something like just like this. This is Foster 1 actually. This is an example of Foster 1. So you'll be able to know whether the network is going to have a pole at 0 or a pole at infinity. That's just basically what it means. That's basically what having a pole at infinity or having a pole at 0 means. So I'm going to show you how to identify those before you even start your synthesis. So what I'll be showing you next is how to identify if the given function would have a pole at 0 or a pole at infinity. So for example, this is an LC function, an inductor and capacitor function. This contains, because it contains only inductor and capacitor. How do we know? We know because the poles and the zeros are located only on the j omega axis. If you plot this on the s-plane, this is the imaginary axis and this is the real axis, right? So for example, this 0 now, for this 0 you have s squared equals minus 4, right? So finding the square root of both sides, you have plus or minus j2, right? Which is what, if you plot this on the s-plane, you have it to be on positive 2 on the imaginary axis and negative 2. So you have the 0 to be located here and that 0 to be located here. Remember, is the numerator, so that's the 0 and the 0. So coming down, you have a 0, you have a pole at 0. This simply means this is a pole. This is a pole because it's on the denominator. So these are poles, while these are zeros, right? The numerator are zeros, the denominator are poles. So it has a pole at s equals 0. So this simply means you have a pole at s equals 0. So coming towards this side, you also have a pole at what? Plus or minus j3. Plus or minus j3, because if you find the square root of both sides, you have a pole to be on positive 3 and negative 3, right? You can see they are on the imaginary axis. You also have a pole at positive, at plus or minus g4, right? Plus or minus g4, because of this plus or minus g4. Square root of 16 is what? 4. So you have it to be on plus or minus g4. So you have it to be what? That's a what? A 0. So you have a 0 on 4 and a 0 on negative 4. So you can notice that the poles and zeros are alternating. You have 0 pole, 0 pole, 0 pole, 0 pole. So it's not like you're having like 0 0 pole pole, 0 0 0 or 0 0 all through. So you're having 0 pole, 0 pole, 0 pole. So it is an LC function. So you can proceed with the synthesis, either Foster 1, Foster 2, Cauer 1 or Cauer 2 form, right? So for you to know whether it's an LC function without plotting the s-plane, all you have to do is check if you have an s term that is carrying a square or a power that is greater than a degree that is greater than 1. So you can see that you're having a square here, so obviously it's an LC function. And to know whether it's a real LC function that you can really actually synthesize it, all you have to do is check if you are alternating this way. For example, now you have a pole at 0. This simply means s equals 0, right? The next one you are having is, so yeah, you are having a pole at 0. So the next one you are having is what? 2, because square root of 4 is what? 2. So you are going from here like this way. So you're having 2. The next one you are going to go is what? 3, because square root of 9 is what? 3. The next one you are going to have is what? 4. So square root of 16 is 4. So because you are going this way, you are going up and down, it makes it an LC function. So it's not like you are going like 0, 2, 3, 4, or probably 0, 2, 3, 4, or anyhow. So it's not like you are going this way. So it's like you are going in a zigzag manner. So which makes it an LC function. Alright, so to actually know whether you have a pole at 0, for like this, what I showed here, to know whether you're going to have a pole at 0 or a pole at infinity, right? From this function, before you even start, you would have known whether you are going to have a pole at 0 or a pole at infinity, which is good for you to know, because after the synthesis of this, using maybe Foster 1 or Foster 2 or Cauer 1 or Cauer 2, sorry, either Foster 1 or Foster 2, if there is a pole at infinity, it will not actually come out in your calculation. It will not come out. So you have to come back to the function and check from the function if you are going to have a pole at infinity, for you to be able to include it in the network after the whole thing. So because you might miss that, because after the calculation, after the synthesis, it will not come out. So you have to come and check here if you are going to have a pole at infinity. But if you are going to have a pole at 0, it will actually come out in your calculation. So for example, if you are asked to find a Foster 1 form of this network, just know that Foster 1, Foster 2 are what? Are partial fraction. They are just partial fraction of the function. Just finding a partial fraction of the function, right? Foster 1, Foster 2, just find the partial fraction of the function. While Cauer 1 and Cauer 2, they are just the long division of the given function, either z of s or y of s. So that's just it. So in partial fraction, the degree of the denominator must be greater than the degree of the numerator. But in LC function like this, in LC functions, you don't need to worry about that. Just go and find the partial fraction straight. So you don't need to worry about that. So you only need to worry when you are dealing with LC, RC network. So when you get there, so you either divide once, then see if you are going to. So if you are having a negative, just add an S term. Just divide both sides by an S term. So that's when we get to LC, RC functions. We explain better, right? So for this now, to know whether you're going to have a pole at 0, obviously, because in partial fraction, you have to separate this into what? A over S plus B over bx plus c over s squared plus 9. So just know that in network synthesis, this c is 0, so you don't need to include it. So all you have to write is a over s plus bx over s squared plus 9, right? And there's a simpler way to go about, sorry, not x, actually s. I'm used to x. So actually x. So there's a simpler way to write this. All you have to do is what? A over s plus b over s. The square root of 9 is what? That's just plus j3 plus b conjugate. That's just the conjugate of this over s minus 3j. You don't need to worry about this for now. I'm going to explain better. So just know that this is how you simplify it to make it easier to find. So what we're talking about, how to know whether you're going to have a pole at 0, right? So because you're having an S term standing alone here, you are going to have a pole at 0. So because you're having an S term below here, right? Because you're having an S term, you are going to have a pole at 0. And because it's a z of s function, what do we say about z of s function? So if the s term is below, right? So if the s term is below, it's going to be a capacitor. So this is just similar to what we have here, right? All you have to do is what? Divide the numerator and denominator by a. Then at the end of the day, the value of the capacitor will be what? 1 over a. So the value of the capacitor will be 1 over a. That's just it. So that's how to know whether you have a pole at 0 or a pole, sorry, that's how to know whether you're going to have a pole at 0. So assuming it was empty, right, it means you are not going to have this will not be there. Assuming you didn't have any s here, right, you will not have any a over s here, which will only include this, so assuming this was Foster 1, this will be what? A parallel combination of a capacitor and an inductor, right? Only this alone. I'm just talking about only this alone. So assuming, so for this particular one now, you are going to be having s, you are going to having a pole at 0, which is the beginning, right, to be what? A capacitor. So all you have to do is include the capacitor, and then, so what we now want to find is if you are going to have a pole at infinity. So to know whether you are going to have a pole at infinity, you have to go back to the original question and check. Once you expand, you don't need to expand, but just look at it. Once you expand with the greatest s, if you expand this, you are going to be having s raised to power 4, right? This s raised to power 4, while if you expand this, you are going to be having s raised to power 3. So you can see that the degree of the numerator is greater than the degree of the denominator, which means you are going to have a pole at infinity. You are going to have a pole at infinity. So according to the rule, it's going to be what? An inductor. So you can check your notes. It's going to be an inductor. So if you are having a pole at infinity, it's going to be an inductor, right? So all you have to do is include an inductor here. So that's how to know whether you're having a pole at infinity. So let me recap what I said. So if you're having an s term below, and once we expand it to its partial fraction form, you're going to be having something like a over s, and this is standing alone. So that signifies that there's a pole at 0. So you can see that there is no clue of whether you're going to be having a pole at infinity or a pole at 0. So you have to go and do to know whether you're going to have a pole at infinity. There is no clue of how to know whether you're going to be having a pole at infinity here. So all you have to do is go and check from the original question if the degree of the numerator is greater than the degree of the denominator. So because the degree of the numerator is greater than the degree of the denominator in this particular question, you are going to be having a pole at infinity to be an inductor. So that's just it. Same for Foster 2. Foster 2 is just the y of s. Foster 2 is just y of s, taking the partial fraction of y of s. So assuming you want to take the partial fraction of this for Foster 2, this is for Foster 1. For Foster 2 now. So all you have to do is what? Swap the position of the poles and zeros. So you have it to be s squared plus 9 all over 10 s squared plus 4 s squared plus 16. I have not actually synthesized this. I just give you the preview of what you are going to be doing. So maybe in the next video I'll actually be synthesizing this, so you'll be able to grab what we are talking about. So this is just y of s. This is Foster 2. So anytime you hear Foster 2, just take the y of s of the given function. if the given function was given in y of s initially, if it was given in y of s, you don't need to change anything, just take it straight up. But because the function is given in z of s, go and take the y of s for Foster 2. So same for Foster 1. If the function was given in y of s, you have to take the z of s. So you swap the position to turn it back to z of s to find the Foster 1. So just know that Foster 1 is z of s, Foster 2 is y of s. So both are partial fractions. So for example, if you want to synthesize this, can you try it to know whether you are going to have a pole at infinity or a pole at 0? So for this, you can see that you don't have an s term, which means you'll be having something like a over s squared plus 4. Let me see, a over j, let me write it again. You have a over s plus j2 plus a conjugate over s minus j2 plus b over s plus j4 plus b conjugate over s minus j4, right? So you can see you are not having an s term. This is not included, so don't be confused. So you can see you are not having an s term here, right? You are not having anything here, which means there is no pole at 0. There is no pole at 0. So that is cleared. So obviously there is no pole at 0. And then at infinity, do you have a pole? You can see that the degree of the numerator is 3, and the degree of the denominator is 4. The degree of the numerator is not greater than the degree of the denominator, which means there is also no pole at infinity. So the network will look something like this. Sorry, this is y of s, right? This is y of s. So the synthesized network will look something like this. So the synthesized network will look something like this. So that will be parallel combination of a series network. That will be the parallel combination of a series network. So Foster 1 is the series combination of parallel network, right? Series combination of parallel network. While Foster 2 is what? Parallel combination of series network. Alright, so in Cauer 1, for Cauer 1, the degree of the numerator must be greater than the degree of the denominator from the highest power. What does that mean? So for example, now if you expand this, you have it to be 8s4 plus 32s squared plus 24, right, divided by s5 plus 6s cubed plus 8s, right? So you can see that the degree of the denominator is already greater than the degree of the numerator. So this, you cannot proceed with Cauer 1, right? So you have to swap the position of these two. You have to swap the position of, so since you are going to be swapping the position, it's going to become y of s equals s raised to power 5, right, plus s raised to plus 6s raised to power 3 plus 8s, right, divided by 8s raised to power 4 plus 32s squared plus 24. So you can now proceed with the synthesis, and make sure you are arranging in descending order. You can see I'm arranging in descending order. This is 5, this is 3, and this is 1. This is 4, this is 2, and this is 1. So for Cauer 1, arrange in descending order and make sure the degree of the numerator is greater than the degree of the denominator before you proceed with your synthesis, right? So for Cauer 1 and Cauer 2, you don't actually need whether to check whether you have a pole at 0 or a pole at infinity. It will actually come out from your synthesis. It will come out naturally after your synthesis, so you don't actually need to worry about that. You only need to worry about that in Foster forms, so you don't need to worry about that. So for Cauer and Cauer 2, they are just ladder forms, so you see them something like, so the synthesis is also always something like this. They're actually ladder network, so it's just like this, so it will continue like that, right? So it will continue this way. So for both Cauer 1 and Cauer 2, so they are actually like this, right? So let's talk about Cauer 2. Cauer 2. So for Cauer 2, let's use the same function. Let's use the same function. So we are using the same function. So for Cauer 2, that will be from the lowest power. The degree of the denominator was greater than the degree of the numerator. What does that mean? So if you expand this, you have 8s4 plus 32s squared plus 24 all over s raised to the power 5 plus 6s cubed plus 8s. So the first thing to do is rearrange in ascending order. Remember for Cauer 1 was descending order. You arrange it this way, but for Cauer 2, you arrange this way. So let's rearrange this in ascending order. That will be 24 plus 32s squared, right, plus 8s raised to the power 4 all over 8s plus 6s cubed plus s raised to the power 5, right? So now you can check for this condition. Now. So the condition says the degree of the denominator must be greater than the degree of the numerator from the lowest power. So this is from the lowest power. So this is from the lowest power. This is the lowest power. This is the highest power because it's carrying 4 and this is carrying 5. So from the lowest power, the degree of the denominator must be greater than the degree. You can see that this is carrying 1 and this is 0. So the degree of the denominator is greater than the degree of the numerator. So which means you can proceed with the synthesis of Cauer 2 with long division. So you can proceed directly. You can proceed immediately. So assuming the degree of the numerator was greater than the degree of the denominator, all you have to do is what? Swap the position, just like you did here. Just swap the position. So after swapping the position, since the function is given in z of s, it's going to change to what? Y of s. So since we are not swapping the position for this particular question, it is still z of s. So you can just proceed with the long division and then you are good to go. And the first elements will be present from the first element or the last element will be present after the synthesis. So you don't need to worry about whether you are going to be having a pole at 0 or a pole at infinity. It will come out naturally in your synthesis. And maybe in the next video I will show you how to know whether you're going to be having a pole at 0 or a pole at infinity for coa 1 and coa 2 before the synthesis, but it's not actually necessary. But maybe in the next video I'll show you how to get it. So that's it. Alright, thank you very much for watching. Don't forget to subscribe and turn on the notification button to get notified anytime I post a new video.